All right, so we are starting the section on electrochemistry, which is the study of electron transfer, and particularly electrons that are transferred that can be harnessed to carry out some form of work. So, the particular reaction class that we're looking at are redox reactions. Remember redox reactions, right? Which involves electron transfer. And because this is a spontaneous process, right, we're looking specifically at spontaneous redox reactions, the electrons that are generated from these reactions can be harnessed to do some form of work, such as lighting a bulb or powering an electric car. So let's review redox reactions since this is what is the foundation of electrochemistry. So remember, with oxidation, this involves the loss of electrons. So electrons are produced, they're written as a product. And the species that loses electrons is said to be oxidized. So in this example here, we have copper solid, which is oxidized. So it produces copper 2 plus, and we write the 2 electrons as a product. With reduction, we gain electrons, right? Electrons are consumed, and whatever gains electrons is said to be reduced. So in this example, we have silver, which gains 2 electrons, or 2 electrons are consumed, reducing silver plus to silver solid, right, which has a neutral charge. So remember our mnemonic device, Leo the lion says grr, right? To remember what happens in our with our electrons in reduction and oxidation. So what I've written here in these examples are half reactions, right? This is an oxidation half reaction, this is a reduction half reaction. In a overall redox reaction, we have oxidation and reduction taking place simultaneously because electrons are being transferred in the reaction. So the reducing agent or reductant, right, is the molecule or ion that causes the species to be reduced. Similarly, the oxidizing agent or oxidant is what causes the species to be oxidized. So the way to think about this is whatever is reduced is behaving as the oxidizing agent, and whatever is being oxidized is behaving as the reducing agent. Both of these, right, both the reductant and oxidant, appear as reactants in the overall redox reaction. So the reason that redox reactions are so favorable, right, or they have by favorable, I mean it has these applications to do, right, to do some type of work that can produce light, heat, all of these technological applications, is because these reactions happen spontaneously, right? There is no work or force that has to be inputted for these reactions to go. So spontaneously, another way to say this is that the reactions go from a higher energy to a lower energy, right, as the reaction proceeds. So think all the way back to thermodynamics, right, when we talked about spontaneous versus non-spontaneous reactions. If something's at higher energy, it can spontaneously go to lower energy without any input of work or force. So because these reactions happen spontaneously, the oxidation state of the two reactants changes, right? So it increases for oxidation and it decreases for reduction. And the last thing I want to say is these reactions have a ton of applications, right? Both biologically or in nature, as well as different industrial processes. I mentioned with powering electric cars, right? So there's many applications where these spontaneous redox reactions are fundamental to some process. So let's look at an example. If we have zinc solid and we dip it in a solution of copper nitrate, what is the balanced redox equation? So pause this video and at least write the two reactants, right? Write the molecular formula for the two reactants and then write what products will be formed. So here's our overall reaction. We have zinc solid in a solution of copper nitrate. This will produce, right, copper solid. So essentially zinc is going to displace copper and then we'll be left with the solution of zinc nitrate. So if we write the oxidation and reduction half reactions, we're just going to write, right, for the oxidation half reaction, what species is being oxidized, and then for the reduction, which of these two species are being reduced. So from this overall reaction, see if you can pause this video and determine which metal is being oxidized and which is being reduced. So zinc is being oxidized. Zinc is being oxidized, right? Because we go from zinc as a solid has a charge of 0, and it goes from a neutral charge to a positive 2 charge because it loses 2 electrons. So this is our oxidation half reaction. Copper is being reduced, right? It's gaining 2 electrons, which is why it's written as a reactant in our reduction half reaction. So we go from copper 2 plus to copper 0, right? To copper with a neutral charge of 0. So this is the reduction half reaction. So zinc is being oxidized and copper is being reduced. Now our overall redox reaction or overall net redox reaction is just the sum of our oxidation and reduction reactions, canceling out the electrons. So this is a pretty simple example, right? If we add these together, we end up with zinc solid plus copper aqueous 2 plus yields zinc 2 plus aqueous plus copper in solid. So here are general steps for balancing redox reactions, right? We assign oxidation numbers. This is important because assigning oxidation numbers will help us identify what is being oxidized and what's being reduced. From there, we can write the two half reactions, right? An oxidation half reaction and a reduction half reaction. From there, we can balance both half reactions, and then we're going to combine them, eliminating the electrons to generate the overall balanced redox reactions. So in the previous example, it was a very simple example. So in the next video, we're going to look at something a little more complex and really dig a little deeper. This is our general steps, but we're going to basically add to this in our next example.